In the late 19th century, scientists observed that a characteristic lavender light was produced when a high-voltage electric current was passed through hydrogen gas. When the lavender light was sent through a narrow slit, then through a prism, it separated into distinct lines of different colors. In 1913, the Danish physicist Niels Bohr proposed a model of the hydrogen atom that explained atomic spectra. The Bohr model introduced the idea of quantized energy states for electrons in atoms. In the Bohr model, the electron moves in circular orbits about the nucleus. According to the model, the electron can circle the nucleus only in allowed paths or orbits. When the electron is in one of these orbits, the atom has a definite fixed energy. While in an orbit, the electron can move to a higher energy orbit by gaining an amount of energy equal to the difference in energy between the orbits. When a hydrogen atom is in an excited state, its electron is in a higher energy orbit. When the atom falls back from the excited state, the electron drops down to a lower energy orbit, and a photon is emitted. The emitted photon has an energy equal to the energy difference between the higher energy orbit and the lower energy orbit. In 1900, Max Planck theorized that a hot object does not emit electromagnetic energy continuously. Instead, Planck suggested that objects actually emit energy in small, specific amounts, or quanta. Energy, he said, was quantized. In other words, the energy being emitted has only certain values, almost as though the energy is a packet. Some wavelengths of light carry only a little energy at a time. Others carry more. But the energy is always quantized. It is always in terms of the packet. The smallest possible amount, one packet or quantum, is defined as the minimum quantity of energy that can be gained or lost by an atom. Quantization becomes important when light or another form of energy interacts with an atom. Sometimes the incoming energy is enough to make something happen, other times it is not. Think of rolling a ball out of a pit. The energy must be enough to get the ball out of the pit all at once, or the ball will simply roll back to the bottom. Even if the energy of multiple rolls would add up to enough energy, the ball will not have been able to get out of the pit because the energy of each hit in itself was not sufficient. With enough energy in a single hit, the ball escapes from the pit. Similarly, if the packet of energy is not large enough, the atom is unaffected, despite the fact that the packets of energy keep coming. If the packet of energy is sufficiently large, however, the atom is affected. An electron, for instance, may become excited. Thomson discovered the electron and proposed the plum pudding model, where electrons are spread on the surface of a solid, positively charged sphere. The discovery of the electron showed that the atom is, in fact, divisible. Rutherford learned that atoms are mostly empty space with negative electrons scattered around a positive center. This model describes a central part in the atom, the nucleus. Bohr's model suggested that electrons move in orbits around the nucleus. Bohr was the first person to be able to explain why atoms could only give off or absorb energy in specific amounts. We now know that electrons are not solid particles that can orbit the nucleus like tiny planets around a sun. In the present model, electrons are found in regions of probability that are often shown as clouds that surround the nucleus at successively higher energy levels. An orbital is a three-dimensional region around the nucleus that indicates the probable location of an electron.
That's right. Since electrons fill orbitals of lower energy first, the 4s orbital must have lower energy than the 3d orbitals.
The principal quantum number n is a positive integer describing the energy level of the electron. For example, an electron for which n equals 1 occupies the first or lowest main energy level and is located closest to the nucleus. The angular momentum quantum number L can be any integer from 0 to n minus 1 and describes the shape of the orbital. The s orbital can be represented by a sphere. The p orbital can be represented by a dumbbell shape. The d orbital is primarily shaped like cross dumbbells, but can also have a fifth dumbbell ring shape. The magnetic quantum number m can be any integer from -1 to +1 and describes the orientation of the orbital. Orbitals run along the x-axis, the y-axis, and the z-axis, as shown in this p orbital. The spin quantum number has only two possible values, +1/2 and -1/2, which indicate the two fundamental spin states of an electron in an orbital. A single orbital can hold a maximum of 2 electrons, which must have opposite spins. It is very difficult to predict the position of any given electron at any given time. There are, however, regions inside the atom where electrons are likely to be, and other regions where electrons are unlikely to be. The principal quantum number n describes the energy level occupied by the electron. When n equals 1, electrons have the lowest energy and tend to be close to the nucleus. When n equals 2, electrons have higher energy and tend to be slightly farther from the nucleus. As n increases, the energy of the electron and the average distance of the electron from the nucleus increase.
The first three quantum numbers describe the energy, shape, and orientation of an orbital. For example, the first three quantum numbers might describe an electron in the 3d x, y orbital. The Pauli exclusion principle states that no two electrons in the same atom can have the same set of quantum numbers. But each orbital holds 2 electrons. So how can we distinguish between these electrons? The spin quantum number distinguishes between 2 electrons in the same orbital. Each electron is labeled with a spin number of either +1/2 or -1/2. The 2 electrons in the 3dxy orbital have different spins. The electron configuration of an element is the arrangement of electrons in an atom of that element. For example, the electron configuration of sodium is 1s2, 2s2, 2p6, 3s1. This orbital diagram shows you which orbitals are filled in the atom. For example, sodium has 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 2 electrons in each of the 2p orbitals, and 1 electron in the 3s orbital. The electrons can be represented by arrows pointing up or down. The sequence for writing an electron configuration usually follows the order shown in this diagram. Each s orbital can hold 2 electrons. Each group of 3p orbitals can hold 6 electrons. Each group of 5d orbitals can hold 10 electrons, and each group of 7f orbitals can hold 14 electrons. By filling in the orbitals one at a time, electron configurations can be determined for most elements.
The Aufbau principle states that an electron occupies the lowest available energy orbital. The Aufbau principle is used to describe the order of electrons in an electron configuration. For example, fluorine has 9 electrons. To find the electron configuration of fluorine, simply fill electrons in to the orbitals in order of increasing energy. First, fill the 1s orbital, then the 2s orbital. That leaves 5 electrons. These will go in the 3 2p orbitals, which can hold up to 6 electrons. That means the electron configuration of fluorine is 1s2, 2s2, 2p5. Electron configuration notation eliminates the lines and arrows of orbital notation. The main energy level is indicated by a number. It is followed by a letter indicating the orbital. The number of electrons in a sublevel is shown by adding a superscript to the sublevel designation. The configuration for nitrogen is represented by 1s2, 2s2, 2p3. The superscripts indicate that 2 electrons are present in nitrogen's 1s orbital, 2 electrons are present in the 2s orbital, and 3 electrons are present in the 2p orbital. This configuration indicates that nitrogen has a total of 7 electrons and tells us that nitrogen has an atomic number of 7. Electron configuration can be indicated by orbital notation. In orbital notation, an unoccupied orbital is represented by a line. The lines are labeled with the principal quantum number and sublevel letter. An orbital containing 1 electron is represented by a line with 1 arrow pointing up. An orbital containing 2 electrons is represented by a line with 2 opposed arrows, showing the electrons paired and with opposite spin. Look at the superscripts for each orbital in the electron configuration. The superscripts indicate the number of electrons in a given orbital. We add arrows to show these electrons. Once all the electrons have been placed, the orbital notation is complete. The noble gas notation provides a way to abbreviate electron configuration. In this periodic table, noble gas notation is used to describe the electron configuration of each of the elements. Aluminum has the same basic inner electron configuration as neon. It differs from neon in that it has 2 electrons in its 3s orbital and 1 electron in its 3p orbital. Similarly, oxygen has the same inner electron configuration as helium, to which it adds electrons in the 3s and 3p orbitals. Writing out the entire electron configuration for iodine would take quite a bit of space. Finding the next smaller noble gas and using it as a base makes the notation much simpler. Iodine has the same inner electron configuration as krypton, plus 17 more electrons.